So here's a main point you're supposed to understand. What does it mean that something is boiling? And that main concept is that boiling is when the vapor pressure of a liquid reaches the atmospheric pressure. The vapor pressure of a liquid increases as the temperature increases. It exponentially increases, and the most common way to get a liquid to boil is to increase its temperature so that its vapor pressure reaches that of the external atmospheric pressure. So here we've increased the vapor pressure by raising the temperature, and we've raised it until the vapor pressure matches the external atmospheric pressure, and in this situation our liquid is boiling. But here is an alternate way to boil a liquid. You could reduce the external pressure on it. So you could put it in a partial vacuum, and it would look something like this. So the external pressure in your vacuum chamber is now low enough that it matches the vapor pressure of your cool or warmish liquid. And I'm going to say liquid here instead of water because this works for any liquid substance. But also in this situation, the water is boiling, even though it might be plenty cool enough to just stick our hand in there and keep it in there. And if it's that cool and boiling, you're probably not going to kill many bacteria in there. So a lot of bacteria might survive 10 minutes of boiling if you're doing it in a vacuum chamber. Now, say instead of decreasing the external pressure, we increase it a lot. So maybe we go under the ocean, and every 10 meters of water is equivalent to 1 atmosphere pressure. So if we go like 1,000 meters under the ocean, that's like another 100 atmospheres of pressure on us. It basically, we have 100 times more pressure. So we jacked up our external pressure a lot, and even if our water gets hot enough that the vapor pressure passes that of what it is at 100 degrees Celsius, it can go 110, 120, 130 degrees and have an even higher vapor pressure than at 100 degrees, but it's still not boiling. It's not boiling because the vapor pressure of the liquid does not match the external pressure. So I've heard of way down in the ocean and hydrothermal vents where you can have water as hot as about like 300 degrees, and it's still not boiling. You still have liquid water at 300 degrees because the pressure is so high. But yeah, we're talking, question 2 for this one. Hydrothermal vents way down, maybe a mile or more under the ocean. But you can find some crazy organisms down here. Ones that are adapted for chemosynthesis, ones that are adapted to live in very hot temperatures. But yeah, that liquid water can get well over 100 degrees Celsius. And yeah, in Denver, that's the Mile High City, right? So most of the atmosphere is closer to the Earth. If you get a mile above a lot of the atmosphere, the pressure is significantly lower, and that's not only going to give less air resistance to a baseball or football, but it's going to decrease the boiling point of water there. So water actually boils at a lower temperature in Denver than at sea level. And let's increase pressure again. That lets the water boil at a higher temperature, so you are giving the bacteria and spores in your tomatoes or pumpkin or whatever you're canning, you're actually getting them hotter with boiling water than if you did not pressurize your container. They in biolabs or a lot of different labs, any lab where you need something sterile, they will probably use some kind of an autoclave, and this is a very secure container where inside is achieved very high pressures and very high temperatures of liquid water. So it's probably a thick metal cube or something like that, and the pressure gets really high in there, so it has to close very tightly. And if you ever watched movies with a submarine, and they're like, okay, open the hatch, and they take the wheel and they spin it like that's kind of what's on the front of an autoclave. And you do not open that thing until it gets cool in there, because if you open it and the temperature is the pressure and temperature are very high, as soon as you open it and the pressure decreases, that very, very hot water over 100 degrees is going to vaporize, and also the pressure that's built up is going to blast out. So you're going to have a lot of steam forming, and you're going to have a lot of pressure release, and it's just going to blast you with super hot steam. When I was in college at Ohio State, the building I did research in, it does not exist anymore, but it had the first floor and then a basement underground and then a sub-basement below the basement. And it was a very, very creepy level, the sub-basement. There's, obviously no windows. Everything is just cinder blocks. It's dank and humid and mildewy. And it's where old furniture goes to die. And in a bare, drab, dank room, small and windowless, they had the autoclave. And there's an urban legend, and it's such a creepy area that you'd believe this urban legend, but there's an urban legend that one time a girl opened the autoclave too soon when it was still hot and pressurized inside, and the steam came out so hot and powerfully that it like melted her skin off her face. But I don't believe it. But heck, it probably maybe could happen. And so as not to leave the video on that note, let's talk about this cool thing. This deserves some attempted explanation. So first, let's understand that when a jet is going near or above the speed of sound, there are significant high and low pressure areas where there's buildup of high and low pressure because of buildup of sound waves, and that you get these condensation clouds in the low pressure areas. The more important thing to understand is that you get condensation when the equilibrium vapor pressure, or the saturated vapor pressure, goes below the actual vapor pressure. So the actual vapor pressure is dependent on the weather today, or in August it's going to be more humid, right? And the saturated or equilibrium vapor pressure is a function of temperature. So therefore, if you get this condensation, the temperature must be going down to decrease the equilibrium vapor pressure. And here's, to the best I can figure, why that happens. In a low pressure area, the air must be less dense, and therefore more expanded. And we know from last semester that when a system of gas expands, it is doing work on the surroundings and therefore losing energy. Now, if this sample of air lost energy, it's going to get colder, and there you have it. When it gets colder, the equilibrium pressure drops, and momentarily becomes lower than the actual vapor pressure of water in the air. And then in order to come to equilibrium again, the vapor pressure in the air must drop, hence the condensation, and you get this condensation cloud.